Hello everyone. In today's session, we are going to discuss one more important concept from discrete mathematics, which is maximum flow problem. And the method that we are going to use for it is Ford-Fulkerson method. Okay, so what we mean exactly by maximum flow problem, as the name indicating maximum flow means what? A weighted graph is given to us, and in that weighted graph, we are supposed to find that how much maximum we can flow. It may be any quantity from the source to destination by considering the restriction of the given problem. Restriction means what? Restriction means what? In maximum flow problem, in a weighted graph, every edge is having a capacity that we call as a weight also. So carrying capacity. So that edge can't carry more than its carrying capacity. So following that each edge should follow or should not carry more than its carrying capacity, how much maximum we can transfer from source to destination. Okay. Now, there are few important points that we do have related to the maximum flow problem. Let us see. So the first thing is what we called our residual capacity. So residual capacity is what? When you are making a path, when you are making a path from source to destination, then how much amount that path is carrying, if we subtract that amount from each edge weight, then remaining capacity for that edge is called as the residual capacity. The second that we do have is augmenting path or augmented path. So what we are supposed to find? We are supposed to find the path from source to destination in a weighted graph. And that path we called as augmented path. Okay, so any path from source to destination which follow the carrying capacity of an edge in a weighted graph is called as a augmented path. The third thing that we do have is known as the bottleneck capacity. So bottleneck capacity is the minimum carrying capacity of an edge in an augmented path. That means when you find an augmented path in a weighted graph, that how much minimum, or better to say, how much maximum amount it can carry through all the edges is called as the bottleneck capacity. How much maximum can be carried, it can also, like we can understand in a manner, the maximum in an augmented path is the minimum carrying capacity of an edge in that same path. The last thing that is the maximum flow. So if we in a graph, if we find n number of augmented path, then the sum of all the bottleneck capacity for all those augmented paths is called as the maximum flow in the given problem. Okay, so these are 3 to 4 things that we are supposed to remember. What are those things? The carrying capacity of a edge, we do have augmented path, we do have residual capacity, we do have bottleneck capacity. Okay, so for more clarity, let us take one example so that we can understand it in a more detailed manner. So this is the problem. We are supposed to find the maximum flow in this problem. We are supposed to find the maximum flow in this problem from the source A to destination 6. From source vertex, as you can see, this is a weighted graph. Yes, this is a weighted graph. What is a weighted graph? A graph in which every edge is having a numerical quantity associated to it is called as a weighted graph. Now, like this is weight 2. So the carrying capacity from 2 to 4 edge is 2. So it can't carry more than 2. The carrying capacity for this is 3, for this is 7, 4, 10, 8, and in the same manner the others one. Since the graph is directed graph, so we are supposed to follow the directions also. If the graph is not directed, then we can move in any manner, like from 2 to 3 or 3 to 2. But since it is directed, so we can move from 3 to 2 by this edge, but we can't move from 2 to 3 in this edge. 3 to 2 is possible, but 2 to 3 is not possible due to the direction restriction. Okay, now how we proceed to find the solution for this problem? So we will list all the augmented path. We will list all the augmented path. So let us make a small table where I list augmented path and its bottleneck capacity also. Okay, because we know that the sum of all the augmented paths bottleneck capacity is the maximum flow for the given problem. And do remember, every augmented path should start from 1 and should terminate at 6 because it is given that 1 is the source node and 6 is the destination node. These augmented paths can be written in any manner. These augmented path can be written in any manner means what? Like the first augmented path I am making, we are starting from vertex 1, then moving to 2, then moving to 4, then moving to 6. Yes, we are following the direction. So first augmented path that I'm writing is 1 to 2 to 4 to 6. Do remember over here, it does not matter which augmented path you are taking first, which you are taking last. Simple thing that we are supposed to consider is what? An edge can't carry more than its carrying capacity. Okay? Generally, we are using our common sense over here and will write those augmented paths where the maximum amount can be carried from source to destination. Okay, just see over here from vertex 1 to 2, 8 unit of a quantity of commodity is carried out. From 2 to 4, it is 2, and 4 to 6, it is 10. Now try to understand that what is the bottleneck capacity for this. We are transferring amount of 8 unit from 1 to 2. Now at 2, we do have 8 units, but 2 to 4 edge can carry only the 2 units of amount. Okay, so at 2, we do have 8 units, but 2 to 4 only carried only 2 units. Now at vertex 4, 2 units comes from this augmented path. 4 to 6, it can carry 10 units, but it do have only 2 units with it. So what is the minimum weight in this augmented path is 2. So the bottleneck capacity for this augmented path is 2. Okay, now adjust the graph. It is having total 8, 2 is used. So how much left on this edge? On this edge, we left with only the 6 unit weight. This is having carrying capacities 2 and used fully. So now this edge is exhausted. We can't use the edge 2 to 4 in any other further augmented path. Okay, any other augmented path, we can't use the word edge 2 to 4 because it is fully utilized and an edge can't be used more than its carrying capacity. This is 10 out of 10, 2 is used. So how much left? 8 unit. This is the residual capacity. So now the residual capacity for 1 to 2 is 6, 2 to 4 fully used. So nothing left with it. 4 to 6, 8 unit left. So those who left with the carrying capacity can be further used. Those who don't left with the carrying capacity, we can't use them again. Okay, now let us try to write the augmented path number 2. So once again, I am taking the path 1 to 2. So 1, then 2. I can't move 2 to 4 because it is closed. I can't move 2 to 3 because the direction is not allowing us to move 2 to 3. But we can move 2 to 5. Yes, we can move 2 to 5. Then 5 to 6. So this is another augmenting path. What is that path? It started with 1, then 2, then 5, then 6. 1, 2, 5, 6. Now, what is the carrying capacity of this? Let us see. So 1 to 2, how much can be transferred? Total was 8. 2 is used in the first augmented path. How much left? 6 unit. So 1 to 2, 6 unit is transferred. Now 2 to 5, the total capacity is 7 unit. But how much we do have at 6? At vertex 2, only 6 units. So 2 to 5, 6 unit is carried out. 5 to 6, carrying capacity is 8, and we do have at vertex number 5 how much? 6 units. So what is the bottleneck capacity for this path? It comes out as 6. Now adjust the graph once again. So now 6 is also used from this edge. This is having total 8. In the first augmented path, we use 2 unit. In the second augmented path, we use 6 unit. So this is completely used. Now 1 to 2 will never be used further. 2 to 5, it is 6, 7, and 6 is used. So how much left? 1 is the residual capacity for this. It is 8. Out of 8, 6 is used. So 2 is the residual capacity for this. Okay, so till now we have formulated two augmented paths, and this is how we find the bottleneck capacity. Let us try to find the next augmented path. Now, 1 to 2 I can't use. So this path is finally closed. We can't use 1 to 2 once again because its carrying capacity is completely utilized and it is closed further. So what other way to move out from vertex 1? We can move in this direction. So let us try to write one more augmented path, which is 1, then 3, then 5, then 6. Or we can write it as 1, 3, 5, 4, 6. We can write any one, any of the paths in any order. So let us write the first at the bottom one, which is 1, then 3, then 5, then 6. The third augmented path in this problem is 1 to 3, 3 to 5, 5 to 6. What next? The bottleneck capacity. So this edge is having 10 units, this is having 12, and this is having 2. Residual is 2, 6 is used. So how much is minimum in this augmented path? 2 units. So the bottleneck capacity for this path is 2 units. So now adjust the graph. This is 2. So total 8 and completely utilized. So crossed it. How much left on this? 2 is used, so 10 unit left on it. On this, 2 is used, so 8 unit left on it. Let us move on to the next augmented path. Now, once again, 1 to 3, we can move 1 to 3, yes. Then 3 to 5, yes, we can use. Can we use 5 to 8? The answer is no, because the edge 5 to 8 is already used. So now we can move 5 to 4 and 4 to 6. So let us write it 1 to 3, 3 to 5, 5 to 4, and 4 to 6. Do remember every path must started from source and must terminated at the destination. So let us see what is the bottleneck capacity for this path. For this, it can carry 8 unit, it can carry 10, it can carry 4, it can carry 8. So how much is the bottleneck capacity? The minimum, which is 4. So in this path, we can carry 4 units. So how much left? Let us adjust the graph. This is 4 further use. So out of 10, 2 and 4, 6 unit use. So what is the residual left for this? 4 units. For this, it is having carrying capacity 4 and complete 4 is used. So this is completely exhausted. So let us cross it. For this, now 4 more is used. So out of 12, 6 is used. So 6 is left for carrying capacity for this unit. And for this much, 4 further is used. So how much is the carrying capacity left? 4 units. Understood? Let us try to make some more. We will repeat this process until unless all the augmented paths are exhausted. Okay. So one more time, let us try to it. So 1, to 3, yes, we can use. 3 to 5, yes, we can use. But 5 to 6, we can't use because already exhausted. 5 to 4 can't use, already exhausted. So if I'm taking this path, I'm unable to make the destination. So leave it. Let us try to take some other path. So 1, 2, 3. From 3, what are the other ways to move out? 5 is not feasible as we already checked, but 3 to 2 is still open. So 1, 3, then 3 to 2, 2 to 5. Yes, we can come 2 to 5. Further 5, if we when we are 5, we are unable to make 5 to 6. So that means still you can see some of the edges having leftover capacity, but we are unable to make the augmented path. So the task is over in this graph. Our task, which is making augmented path and bottleneck capacity, is done. No further path is exist. No further augmented path exists in this graph. So we'll stop the process. Now, what will be the maximum flow in this problem? As we discussed, the maximum flow is the sum of all the bottleneck capacities. The sum of all the bottleneck capacities. So what is the sum? 2 plus 6 plus 2 plus 4. 8 to 10, 14. So 14 units. So the maximum flow in this graph by Ford-Fulkerson algorithm is 14 unit. I hope you understand it. The thing is that I have drawn 4 augmented paths. It's not necessary that when you draw it, you will also get 4 paths. It may, like I have taken first path as 1, 2, 4, 6. You are not interested in 1, 2, 4, 6. You can take first path as 1, 3, 2, 4, 6. That is also okay. No problem in it. Ultimately, you can have the different augmented path, you can have different number of augmented paths, but ultimately your maximum flow will always unique. Okay, note this point with you. The maximum flow in a problem is always unique. You may have the different augmented path, you may have the different number of augmented paths, that does not matter. I hope you understand this problem. Let us take one more problem so that you get more clarity. So over here, we are supposed to find the maximum flow from source node A to the destination node F. In the same manner as previous one, so let us make a table, serial number, then augmented path, then the augmented path, and the third one is bottleneck capacity. The first augmented path, we can do it in any manner. So there's no need to worry that should I start from A to B first or A to C first. It's totally your choice. Earlier we start on the upper side. This time let us start on lower side. The first augmented path that I'm going to make is A to C, C to E, and E to F. So this augmented path is listed as A to C, then C to E, and E to F. When you are making augmented path, do remember that you are supposed to follow the direction if direction is given. Let us see the bottleneck for this. So this is 8 unit, this is 8 unit, this is 2 units. So the minimum is 2. So the bottleneck capacity for this augmented path is 2. Let us reduce the graph. So 2 is used. How much left for this? 6 unit. It is having 2 unit and 2 completely exhausted. So close this edge. This is also having 2 and 2 is completely exhausted. Close this edge also. So this is what one of the augmented path that I have. Now can I take A to C again? Let us try to see. A to C. I do not have the path to move out from the vertex C because C2E is already exhausted. C2E is already exhausted. So there is no further path by taking A to C direction. Understood? Now, what are the other paths? I can take A to B path. Yes. So let us write the second augmented path, which is A to B. Now on B, we do have two paths to move out, A to D and B to D and B to E. If I take D, then I should take F further to move out to the destination. Let us take this path, A to B, B to D, and D to F. What is the bottleneck for this? Yes, the one unit, the minimum of all these weights, one. So if you take this one, this is closed. If you take this one, residual is 4. If you take this one, residual is 1. The bottleneck for this is only 1 unit. Let us check the other path. So is there any other path exist? A to B, B to D, D to E. But from E, we can't arrive to F. Let us try to other A to B, B to D, D to E. We can't arrive to F1. So in this simplest problem, only two augmented paths are there following the bottleneck capacity or carrying capacity for every edge. So only two augmented paths. The task is done for finding the exhaust, finding the augmented path along with the bottleneck capacity. What is the maximum flow? The sum of bottleneck. So 2 plus 1 is 3. So the maximum flow for this problem is only 3 units. I hope you understand it. Simplest way to find the maximum flow is what? You can draw the graph repeatedly after every augmented path. That can also be done if you are having confusion that how much residual is left over after every augmented path. If there is no confusion, the same alteration can be done in the same graph as per the augmented path, as per the augmented path. I hope you understand it. Now let us close this session.